Welcome. Today we're going to talk about Laplace's equation in polar coordinates. That's one of our objectives today. And the other objective is to talk about a property of solutions of the Laplace equation, which is called the zero-net-flux property. And this is really a consequence of the divergence theorem. So let's talk about these two goals and why we want to put them together. First of all, we want to talk about some of the qualitative properties. Of solutions U such that the Laplacian of them is 0. Okay, so we want to know more if our function u of x comma y solves the Laplace equation. What can we say about u? Are there some interesting properties to that? We know that it's the equilibrium temperature distribution. We also know it's the electrostatic potential. There's lots of interesting things about solutions to the Laplace equation. One of those is this idea of a zero-net flux. And we're going to talk about that. So let's achieve that goal right now. And the next thing we're going to do, so that's the first thing we're going to do. And the second thing, we're going to use that. We're going to use one to derive the Laplacian in polar coordinates. So we know, for instance, that in Cartesian coordinates we can write down the Laplacian as just the second partial with respect to x and the second partial with respect to y. But what if we define u in terms of r and theta, right? So now we have a different way of representing it. Naively we could think that the Laplacian in this case it would just be u r plus u theta theta, but that turns out to not be true. And we're going to actually use the zero-net-flux property in order to derive it correctly. So we'll figure out a good representation of what the Laplacian is. So what is that zero-net-flux? We'll get back to that. All right, so the zero-net-flux just comes out of the divergence theorem. Recall that we have what I want to do is talk about if I have u, and I'm going to take its. I want to find out. I want to look at the gradient of it. So this is the gradient vector. So that's our gradient field, defined by the gradient of u. We want to talk about the flux in some through some region D. All right, so I'll put that here. There's my D. All right, so this is this will be in X and Y. But we could just as easily put a z dimension on this and make this a three-dimensional thing. And so the boundary of D we're going to call partial D, and that's just going to be this thing here. We want to talk about the flux through it, so we take little normals, right? At every point, we take little patches of the if you think of them as patches, and make normal vectors for each little line segment. So on and so forth like that, all around. All right, and then what we do is the total flux is simply going to be the closed integral partial over the partial of D, the boundary of D, and it's going to be of the gradient dotted with that normal ds. So recall in 3D, this same integral would be a double integral partial of D. It's the same notation. But instead of talking about a little length segment of our, that would be our ds there, it'll be a little surface area patch over a three-dimensional volume. So it's the same exact analysis. And we know from the divergence theorem, we can rewrite this as the integral over the area of the divergence of the vector field. And we know that is precisely the Laplacian, which we know because this thing in here is 0, because we're defining it as such. Right? U is a solution to the Laplace equation. So that means it's 0, and that means the total flux, or the net flux, over the boundary is always going to be 0. All right, and we can do the same thing in 3 dimensions, and you're probably more familiar with that. And then it's an integral over a volume rather than an area. And that, of course, is also and this is just the Laplacian in 3D, which we know is equal to 0. And the integral of a function that's 0 over whatever volume is always just going to be 0. So what this says is, well, we might have some thermal flux or some electric field flux going out, there'll be an equal and opposite amount of flux going in somewhere on some other portion of the boundary. So whatever goes in, there's some other area that has some other part of the boundary has as a flux inward for every portion that has a flux outward. So the net balance, or the total flux, is always going to be 0. Okay, so that's a property of, and this is true for any region D. So this is through some region right here. What we mean is any region that's in the domain of interest. Okay, so this is true. Any closed region inside of our domain of interest, we find out that we have zero net flux. So again, this is the same thing as saying that this means divergence free. Okay, so that's just a nice property of the Laplace equation. Now we're going to use this to achieve something else. So now, of course, we want to talk about polar coordinates. Okay, so how do we write the Laplacian in polar coordinates? So there's a really special or a straightforward way of doing it, right? Where you take x, and of course you use your polar coordinates, cosine theta, and y are sine theta. And then what you have to do is do a bunch of transformations in order to transpose every derivative. So uxx becomes something, and uyy becomes something as well. We're able to relate all of our derivatives in x and y into some sort of form of derivatives in terms of r, and also some derivatives in terms of theta. So how do these actually work? How we go back and forth between these? We can do this by doing a change of variables. However, it's fairly complicated, and it's not very enlightening. So instead, what I'm going to do is I'm going to use, so our goal here, we're going to use the zero flux property over a small region, which I'll call D, to discover what this Laplacian is in polar coordinates. Okay, so that's the goal. All right, so what's this region D that we were going to talk about? Well, why do we want to do polar coordinates with our Laplacian in the first place? Well, the straightforward answer is if our region E that we want to solve of the Laplacian on if is a disk or an annulus. So we have something like this. So that's E. And then we have the boundary of E is then, of course, just a is just the outer circle here. So we want to, if we're trying to find the solution to the Laplace equation on a boundary like this, it makes sense to go to polar coordinates to do so, and that's why. Okay. Or we could also do it on some annular region where maybe we have the circle or the inner part bored out. So that's the annulus, or a circle, or some sort of disk. All right. So what to do now? What we're going to do then is, so a small little patch then of our disk shape will be some sort of little polar square. So our polar wedge will be of the form, here's the center of our circle, of our disk. We're going to bring it out like that. Oh, I'm going to redraw that. And we'll say that R is going to range from A all the way to R equals B. Likewise, alpha, or sorry, our angle theta is going to angle, it'll vary as delta theta, right? So if this is our little region, I'm going to call that D. We know that there's going to be, if I take the partial of this region, the edge of it, if that's the region inside, and the edge is just this boundary, we know that from the zero-net-flux property, we have the gradient of u dotted with the normal. So we have a normal on that side, and a normal on this side, and a normal on that side. Dotted with the normal vector, ds is going to be 0, right? So what remains to be solved is, now we'll assume for now that the angle we're sweeping over is small, and this side we'll call delta r, and that's also small. And in doing so, and because we know that our function u, our solution to the Laplace equation, varies continuously over time, it's a smooth function, we know that as long as we make delta r and delta theta small enough, we can find at least a good approximation to the flux integral that we could set it equal to 0. And then what we do is we'll take delta r and delta theta, both going closer, smaller and smaller and smaller, and that will firm up our analysis. So again, that's the idea. Okay, so let's go to initiated paper. I'm going to rewrite my little annulus here. So the zero-net-flux property means that, so what again is flux? It's going to be equal to, because we're talking about the Laplace equation, it's going to be the gradient across the boundary, and it's going to be times the length segment of the boundary. And we have 4 boundaries here, four pieces that make up the total boundary. So we have 1 and 2 here, these 2 sides. We also have 3 here and 4 there. All right, so how do I get the flux across? So what is the gradient across the boundary? So we need to find the gradient here. So let's try finding the gradient. I'm going to erase that there and just relocate it here over in this corner here. That's 1. All right, I need to find the gradient, the local slope. I want to find the local gradient of u. So we know that has to be the partial of u with respect to r. And we want to find the flux into this boundary. Okay, So that local gradient, then it has to be, if we have if the concentration is going up, or if the value of the temperature is going up, then we know that the flux is going outward, right? So we have to put a negative there. So that is so this represents, so I shouldn't say the gradient across the boundary, I should say the gradient, I'm sorry, I misspoke. I should say this is the flux determined by gradient. Per unit length. And then we multiply it by the limit, and then we get our total flux. All right, so sorry about that. So again, if our value of u is going up inside and it's going down as we go outside, then the flux will be going out, and that would cause a negative flux, so I have to put a negative sign there. And now what we have to do is, and we'll assume again that this is smoothly changing, and so as long as our patch here is small enough that we can take this value to be, we'll just take one representative gradient value here, and we'll represent it over the entire extent of this little angle sweep here. So we know then that the length of that side, then, the length of 1 is going to be r times delta theta. Okay, so I can put that there, r times delta theta. Okay, so that represents just the flux going into our region on the side 1. So what about the side 2? Well, it's going to be the same thing, but now it's going to be r plus delta r times theta. That's our length segment of the boundary. Okay, and again, that's when r gets bigger. Of course, for the same sweep of angle, we're going to have a bigger line segment there, and that's simply because we've gone up in radius, right? So that's delta r on this side. All right, and then because now if u is bigger on the outside than the inside, so the local gradient is going like that. It's going from a high value to a low value as you go across, then it should be the positive partial derivative. But we're going to evaluate this now at r plus delta r theta. And here, this is just evaluated at r theta. Okay? All right, so now we have the flux going through these two sides. Might as well get the third now. So the third now, we have to think about the local gradient on this side. So on this side, we have, how do we take a derivative going here, across there? Sorry, that has to be r. We take the derivative with respect to r here because we're going in the radial direction. But now we're going to take derivatives going in the angular direction, because we want to know the gradient going across this side here. And so if I want to take a local gradient, I'm going to, on this side here, it's going to be just like before. If u is bigger on this side and it goes down on that side, then that's going to cause a flux going out, which is going to be negative. So we have a negative partial of u with respect to theta. But we have to do one thing, is we have to multiply by 1 over r to take into account that our gradient, as we go across here, the amount we go across depends on the radial distance from the origin. So we have to put a 1 over r multiplied by that. We're going to evaluate that at r. We'll just evaluate it r somewhere in the midpoint there. We'll just evaluate it here. And then we have to evaluate that at theta. Okay. So now for 4, it's going to be very similar. But it's going to be up, just like before how the signs change, we're going to have a 1 over r, but it'll be a positive partial of u with respect to theta. But we're going to evaluate that at r and theta plus delta theta. All right, and what do we have to do to these? We also have to, oh, I'm sorry, I forgot one thing. We have to multiply by delta r, right? Because that was the length of the boundary side here. That was delta r, right? And the same thing here, we're going to multiply by delta r. All right, what we knew then is that, so now we're going to put all these together. Okay, So what we know is if I integrate over d, and I know here's my Laplacian, and whatever its value is over dA, but as long as my d is small, we can make it as small as possible by taking delta theta and delta r going to 0. Then what I can do is I can factor that out because it's essentially a constant. It's also a constant that happens to be 0, but bear with me on that. The idea is that as long as u is smoothly varying, if we take a small enough patch, then our Laplacian shouldn't change value very much at all. So we can do that, and that of course becomes partial of u with respect to, and now we have to think what's the area of d, because that right here is the area of d. So that we can approximate it as going to be simply r delta theta, right? Okay, so that's nice. Now on the other side we have that flux. Which now we have to add up all the sides. We have to add up 1 plus 2 plus 3 plus 4. Okay? And that's going to be, we just have to add them all up. And we'll do it this way. First we have a delta theta, and that's going to be an r plus delta r. And then we have a partial of u with respect to r plus delta r, comma theta, minus r partial of u with respect to r of r comma theta. Okay? And then we go plus 1 over r delta r. And now we have to, so that was 1 and 2 we just did here. And then we have to put these in there. We have a partial of u with respect to theta r theta plus delta theta minus partial of u with respect to theta r theta. Okay, so we see we have this thing here, and we're going to divide that through now. So now we're going to get, I'm going to rejigger our calculation a little bit. We're going to get the Laplacian of u is equal to all of this stuff, but we're going to divide by r delta r and delta theta. We see here the r's cancel. We can cancel that and put an r squared there. We see then we have a delta theta down there. The same thing here. That cancels with that theta, and we leave those alone. Now, putting that all together, we see as we take delta theta and delta r going to 0, notice that this is somewhat like a derivative. We're going to have to go to a new sheet of paper here. So we have the Laplacian operator is going to be equal to r plus delta r partial of r u with respect to r plus delta r comma theta minus r partial of u with respect to r at r of theta, all divided by r delta r. All right, so and then in addition to that, we also have 1 over r squared times the partial with respect to u of theta evaluated at r and theta plus delta theta minus the partial of u with respect to theta evaluated r theta. all divided by delta theta. All right, so as we take delta theta going to 0, this right here, this term becomes 1 over r squared. Just put an arrow going there. 1 over r squared. And this is, of course, the second partial with respect to theta. And this term is a little bit more complex, so I'm going to move it down here because we have this r dr hanging out around there. So what I'll do is I'll put that 1 over r just out front for a little bit. And what I want to do then is, and we have that, and we still have that delta r there. I'm just going to do a little bit of factoring here. So we have a delta r, partial of u, and then we have plus, and I'll factor that, okay. So that's a delta r down there. And so clearly this r cancels with that r, and we're left with a 1 over r. I'm just going to put the partial like that. That's just a ur, the derivative of u with respect to r. And then if we look over here, we get a, the r's cancel, and we're left with, and we have this delta r. I'm going to factor that in there after we cancel that. And that'll, of course, just be, and then the r's will cancel here, and we'll get just the second partial of u with respect to r. Okay, and that's as delta r goes to 0. Right? We can rewrite this a bit, actually, and this is just this is a totally fine way of doing it. That that we just have to put this together, and there's a little bit more of a clever way to put this together, and that's. And we can see that this actually equals the top by reversing the steps, by doing the product rule here. Like so. Okay, so there you go. So if we put it all together, after we've taken all the limits, the Laplacian we have discovered now is going to be 1 over r, the partial with respect to r, of r times the partial with respect to r again, plus, and here's that term up there, 1 over r squared, partial of u with respect to theta. The second partial of u with respect to theta. Okay, so that's the formula for the Laplacian in r and theta. So there's your answer.